the sort of problem that we're interested in. Okay, I accept the recording. There we go. Okay, so a very general question is, so we want to think about a very complicated, some model of a complicated random analytic function and a curve, and we want to understand how small the function can get on this curve. There's been a lot of work on the distributions of zeros of random analytic functions. So looking at the point process of zeros, we're doing something that is similar. I mean, there's a lot of techniques, but the tools that we use are sort of overlapping. But instead, what we're doing is we're fixing a curve, and we want to look at this analytic function on the curve and understand how small it can get. And then more than that, so rather beyond just understanding the distribution of the global minimum, we would want to have some understanding of the process of near minimizers. And so it's sort of, if you have the global minimum, are the other near minimizers kind of in clusters nearby, or do you kind of have near minimizers very well separated and kind of independent? So our model, what we do is we address it sort of a whole class of so-called trigonometric polynomials, but for the talk I'll just focus on the so-called catch polynomial. So this is perhaps the simplest model of a random polynomial you could think of. Is just to you just have IID standardized coefficients. So I have degree 0 up to n. There's n+1 coefficients, so I have a whole sequence of them that are IID centered unit variance, and we'll take them to have nice tails. The philosophy here is that they just have to be nice enough, and we don't really want to think too hard about it, so we'll say sub-Gaussian. What ends up being really important for this problem is not tails, but actually anti-concentrations, so small ball estimates. Don't pay too much attention to the tail hypothesis. It's just we need some tails, some control on tails. Okay, so there are other models of random polynomials where you have some weights that decrease, but because these don't decrease, so they're all the same size, it's not hard to see that most of the zeros of this polynomial are going to be really close to the unit circle. And that's because if the modulus of z gets to be a bit larger than 1, then the degree n term dominates the rest. It's exponentially large. And then if you go a bit inside, then the C0, the behavior C0 dominates, and it's hard to get enough cancellation from the other terms to create a zero. So this polynomial is going to be, it's going to have its zeros clustered near the circle, but we're not going to look at the process of zeros. We're going to look at how small this function can be on the circle. You can think about, in the literature on random polynomials, there's really just two distributions that are the most important, and they're kind of require different sets of techniques. So there's the Gaussian and the Rademacher. And I'll be talking about our results, sort of what goes into proving our result. In the Gaussian case and the Rademacher case, it requires a very different set of tools. Okay, so are there any questions about the model, what I mean by this random polynomial? Okay, so yeah, let me just make sure I have my windows. Okay, so as I was saying, there's been a lot of work on distribution of zeros, and in particular, if the coefficients are themselves real, then of course the zeros come in complex conjugate pairs, and you might expect that a lot of them are actually real. And that turns out to be the case. There's a growing number of zeros that are real, and there's probably most of the literature on these sorts of polynomials has been on counting the number of real zeros. So this goes back to, so the 30s and 40s with Bloch and Polya and Dawford, they're looking at the Rademacher case, or various discrete distributions. And then Katz looked at the Gaussian case, and with this this Katz-Rice formula, was able to get a really precise asymptotic. So it's asymptotic to 2 over pi log n. Zeros are real. Okay, and then there was subsequent work that sort of generalized away from the Gaussian to, more, I think it covers sub-Gaussian at this point. But there's just a huge literature on that, and so I'm only able to list up to 1980. I just decided that was a reasonable cutoff, because otherwise it would just be the whole page. Also, I don't want to talk about it too much because that's not our problem. So what we want to look at. So here's a sketch of what's going on. So as I said, most of the zeros are close to, so we have n zeros for this random Katz polynomial. Most of them are very close to the unit circle, and it's not hard to see that they'll generally be a cluster at a scale of order 1 over n from the circle. Okay, so, and then, so we're going to be looking at the function on the circle, a very closely related problem that's also been considered recently, and that we're actually working on now, is to look at the process of nearest roots. So you can look at, so nearest roots to circle. So you can look at this, the collection of, so say that I call the zeros zeta j, and then I look at the distances of these to the circle. If I want to think about how, it's not, so you would guess that if all of them are at scale 1 over n away from the circle, and you have n of them, and so you sort of have n different tries to get really close, then the nearest one is going to be at scale 1 over n squared. So the closest roots to the circle are going to be at scale 1 over n squared. So if you scale up by this, okay, so this is just a collection of points. Okay, so this is, well, okay, I'll be imprecise. This turns out to converge to a Poisson point process of intensity 1 over 12 so this is a result from last year for the Gaussian case of the coefficients, and that's of Michelen and Sahasrabutta. Okay. Okay, so in the Gaussian case, they were able to show that, so if you scale up by n squared, then you'll see boundedly many points within a bounded neighborhood of 0. And it's a Poisson point process, these distances. Okay, and so it's closely related to what we're doing, because you could imagine that if there's a 0 very close to the circle, then the polynomial will be small on the circle near that root. And so actually what it's sort of, well, this will appear soon, but we can actually generalize this to general sub-Gaussian coefficients using our approach. Okay, so our problem is the minimum modulus. So I want to rescale and reparameterize my curve, or my polynomial, in this way. So since we're on the unit circle, I'd rather parameterize by an interval. So I write e of theta for e di theta, and then when you're taking the jth power, this becomes this wave of frequency j. So now it really looks like a trigonometric series. And then I also want to scale by square root of n plus 1, just so that this polynomial, so at each fixed t, this is a Gaussian, a standard Gaussian. So this is okay. So if they were Gaussian, so so that this standardizes the variance. So it's a centered variable with variance 1. Okay, so this is an order 1. So this just scales it so that this is of order 1 in probability. Okay, and then and so what we're looking at is the minimum modulus of this function. So this we're not the first ones to wonder about this. This is so Littlewood asked about this, I think, in the 40s. And so what he conjectured, so he made a very modest conjecture. And I think this was not the bravest conjecture, that that this min modulus should be going to 0 with high probability. Okay, so you have this Gaussian, okay, if they're Gaussian, so you have this random process on the interval minus pi to pi, indexed by t. It's order 1. But as we'll see, it's a pretty choppy function, so that you might imagine it decouples pretty quickly, so that you get a whole lot of independent tries to be very small. So I think it's certainly believable that the global minimum would be going to 0. Okay, so that was his conjecture, and that was confirmed by Kashin, who showed that the probability, so that it's at most inverse logarithmic in size, so log n minus 1/3. Okay, so the probability of that goes to 0. Okay. All right, so that confirms the conjecture, but actually it's much better than that. So Konyagan showed that actually he showed that it goes to 0 almost as fast as 1/n, which we'll see is actually a natural guess. So this is for any positive epsilon. And then with Schlag, they were able to get a lower bound on sort of a lower tail estimate, so that the probability that this is smaller than epsilon/n for any epsilon is bounded by epsilon up to constants. So these two results here. So this says that, you know, if this converges to a limit, if mn times n converges to a limit, then it'll have a bounded density. At least it has a bounded density near 0. So that's what this result says. And here it says it can't get too much larger than 1/n. So it seems like this is, you know, if you multiply by n, then this might converge to some random variable. Okay, and so that's what we've been able to show. Okay, so we first started talking about this. Hoi and I were with Ofer Zeitouni at a AIM conference, and sort of some ideas came out of that, and then he went and found a great student, Oren Yakir, and I think he might be at Weizmann, and they completely worked out the Gaussian case with this really beautiful argument that I'll describe soon. And then Hoi and I proved a corresponding universality result. So their result says that this minimum modulus, when you scale up by n, converges to an exponential random variable of rate 2√π/3. And our result, so that's for real or complex Gaussian, and then we extend this to any sub-Gaussian variable, and it's a really it's a universality result in the true spirit of a universality result, is that we don't just generalize their proof. What we show is that whatever the answer is, it's going to be the same as the Gaussian. So our proof does not give a new proof of their result. It's, if you take them together, then you get this limiting exponential distribution under these general hypotheses on the coefficient. As I said, the sub-Gaussian it's convenient, but it's, you know, if with a bit more sort of technical work, some sufficiently high moment would suffice. But as I said, this problem is not really about tails, it's about anti-concentration. So are there any questions about the statement? Okay, so so one thing that I will say that so I mentioned before that there's the two important cases are the Gaussian case and the Rademacher case. And with the Gaussian case, you have all kinds of tools available. And with the Rademacher case, you don't have those, and there's certain arithmetic difficulties that come up that aren't in the Gaussian case. So the proof ideas for extracting the limit in the Gaussian case are kind of orthogonal and very, very different from what's required to get this universality result. And the Rademacher case, you really need our entire proof for the Rademacher case. So the Rademacher case, I mean, we do the general sub-Gaussian, but the Rademacher case really captures all of the difficulties. It's, you know, if you had some better sort of small ball estimates, you know, if it were slightly better than discrete, you wouldn't need the whole proof. But for the Rademacher case, you really need the whole proof. All right, so I'll describe some of the ideas for both of these proofs momentarily, but before that, I want to draw some parallels with another sort of what's been a pretty hot topic lately. So we're looking at the minimum modulus for high degree random catch polynomials on the circle. Another big problem lately has been to look at the maximum modulus for a different sort of random polynomial, the characteristic polynomial of a random unitary matrix. So a unitary matrix, of course, has all of its zeros on the circle, so the minimum modulus question is pretty trivial. But if you want to understand the maximum modulus, it's pretty interesting. If you take the Haar measure for these matrices, then okay, so then you have this characteristic polynomial, which again I'll parameterize by the interval, so by this real variable t. It's well known, or you may have heard of this neat fact that characteristic polynomials, the characteristic polynomial of a large Haar unitary matrix seems to be a great model for the Riemann zeta function at sort of a random height on the critical axis. So this was noticed. So there was Montgomery and Dyson some decades ago noticed that Montgomery had a formula for correlations between pairs of zeros of the zeta function, sort of this is in a statistical sense. So if you look at a random height at order capital T, he had a correlation function with which Dyson recognized from his work on random matrix theory. And it's a big problem to actually prove anything, to actually rigorously establish a connection here. So these have been studied a lot because they model this function. So you can take an interval of size 1 or 2, say, and randomly shift it at scale capital T, and then look at this function, this the Riemann zeta function in this randomly shifted interval is now a random field. It behaves a lot like a high degree random polynomial, and in particular like a unitary matrix. The analogy is that so you just log t here if you replace with n. So the parameter n, the correspondence goes with if you replace n with log t, then you can sort of prove theorems here which kind of manufacture conjectures about the zeta function. So this is kind of a big industry, is producing conjectures about the zeta function by proving theorems about this polynomial. What's been well known for a long time is that the zeros of the characteristic polynomial, so the eigenvalues, behave a lot like eigenvalues of the zeta function. But what's neat is that actually the analogy extends to extreme values. So if you look at the extreme, very large values of this polynomial, they behave like large values of the zeta function. So it's in the zeros and in the extremes. This whole function is a good model. Okay, so there's just been a huge amount of work on this lately. So there were 3 teams that got very precise results on the level of the maximum modulus. And I won't state any results here. I don't want to get too far afield. But so there were these 3 teams that established the level of the maximum in increasing precision. And then there's been subsequent work of Argan, Bourgade, and Radziwi, and then also with Belius and Sound, have established analogous results for the zeta function. Actually, not unconditional results, so it's not assuming the Riemann hypothesis. These all follow, there's this really fascinating connection. It turns out that these random functions fall within this class of log correlated fields. And there's a whole paradigm for studying extremes of log correlated fields that's based on ideas that Bramson had in the 70s for studying the leading edge of a branching Brownian motion. Okay, so that's that whole literature, and now I just want to make some parallels here. So when you look at the max modulus of a random polynomial, like the random trigonometric polynomial, to understand the distribution of that or the level of that, it really is all about large deviations principles. So you need to understand how quickly the field decorrelates, and then you want to look at the joint distribution, sort of, you want to get joint large deviation principles for the height of this field at different points. And then there will be a competition between how many tries it has to get very high and what the precise tail is at each point. And so, so you'll have a union bound competing with the tail that you have from the large deviation principle, and that's exactly what determines the maximum. Okay, and then with Bramson's ideas, you do this neat, there's this really nice sort of subtle truncation argument, truncated second moment argument, coupled with LDPs that get the level of the maximum. For us, when you look at the min modulus, it turns out it's all about joint central limit theorems and anti-concentration. So for max modulus, it's all about large deviations principles and concentration. Here it's about central limit theorems and anti-concentration. We also use the moment method, but we actually have to get all moments, although we do some truncation, but it's not really as subtle as this one. And then again, I've said that the ideas for the Gaussian case and the Rademacher case are quite different, and the field behaves quite differently. And there's an analogy over here in the literature between the Haar unitary matrix. So in the Haar setting, you have well, one thing that helps you is that you have this sort of smooth distribution, and then there's also a lot of miracles. So Haar unitary matrices are just there's just a huge number of beautiful miracles that happen with these, and so much that these 3 results here, these 3 teams, all used completely. Their proofs are completely different. I mean, they use completely different perspectives on Haar unitary matrices. Okay, and so the analogous sort of discrete type question over here is something that I looked at with Ofer Zeitouni, where we looked at determining the level of the maximum for the characteristic polynomial of a random permutation matrix. So rather than the smooth Haar distribution, draw it uniformly from a discrete subgroup. So in both of these cases, so in the Rademacher and the permutation case, the field behaves badly or erratically near roots of unity. Okay. Whereas in the Gaussian case and in the Haar unitary case, the field is stationary under rotations. So so you don't have this difficulty. Okay. So that's just you may have heard of these of this literature lately. So I just wanted to make some parallels. Okay, so now we'll talk about some of the ideas, and I want to spend some time talking about Yakir and Zeitouni's work, because it's a really nice argument. Okay, so I'll be talking about both. The first step is kind of common to both of our arguments. Is our approach to this problem is to find a point process of approximal. Okay, so morally, why do we get an exponential distribution in the limit? Well, it's really because of more specifically, what we show is that if you look at the local minima, these local minima roughly follow a Poisson point process of intensity square root of pi over 3. And so then when you look for the global minimum, then you're just taking, you have a Poisson point process of this intensity on the line. What's the distribution of the closest point to a given fixed point? So that'll be exponential with rate 2 root pi over 3, because you can be close to it on either side. Okay, so that's really what's going on. Is we're going to try and find a way of extracting this point process of approximate local minima, which are, again, as I said, at scale 1 over n. Okay, so all right, so our first step is to discretize. So we're not going to look at the function on the continuum minus pi. We have to discretize. So what we'll do is so we'll look at the polynomial. Okay, so the polynomial. Okay, so I actually have it down here. So this polynomial fn, so recall this trigonometric polynomial, we'll look at it on a discrete set. So I'll label these points t alpha. Alpha equals 1 to n. Okay, so so these will be evenly distributed. Okay, so we're cutting the circle up into capital N many arcs, with capital N is going to be, so it turned out we want it to be almost like little n squared. Okay, so the idea is, so we want to capture the moment when this polynomial is closest to 0. You can see, it's not hard to see, that the derivative of this thing is going to be of order n. Right, so this is this random variable at any fixed point is of order 1. When you take a derivative, it's of order n, and so it's going to be varying at scale 1 over n. And if you're going to want to see what's going on, if you want to capture these arcs that are sort of zooming in close to the origin, you're going to need to look at it on a mesh of points, certainly that's growing faster than n. But it turns out we need it to be almost n squared. Okay, so this was also done. This was also done by Hoi Nguyen and Schlag in their work on the lower tail. So they similarly they similarly chose a net of about this many points. And then what they did is they do a careful union bound. So you look at, at any fixed point on the circle, you get some upper bound for the probability that the polynomial is small there. And so you'd like to just do a union bound over this many points. You can't do that because the quality of your sort of small ball estimate, the quality of your bound on the probability that it's small at some given point depends on proximity to roots of unity, as we'll see. And so it's not as simple as taking a single union bound. You kind of have to categorize points and sort of do like a stratified union bound. So it's a careful union bound. But we're going to have to go a bit further in order to capture the distribution of the minimum modulus. So let's see why. So just to give you a picture. So again, here's my normalized polynomial. So this is a function that maps this interval minus pi into the complex plane. And we're looking at how close, so you get a random curve in the complex plane. So you sort of have a particle whizzing around. And we're looking at the closest it gets to the origin, which is at scale 1/n. And in order, so it looks like, among all these curves, okay, I guess it looks like the minimum modulus happens here on this loop. So we want to capture that moment. We want our mesh to be fine enough that we actually sort of roughly capture this moment when the particle is closest to the origin. So we have to take our mesh sufficiently fine. Okay, and these things are very, the derivative is n, so you can sort of see it's varying at that scale. So here's our mesh points, and they're mapped in here. Now, we need to take the mesh sufficiently fine in order to capture this moment that it's close. But if you were to just do a union bound, the union bound's not going to work because it'll be wasteful. Because when one of these points is close to the origin, it brings a whole cluster of them. This entire loop they'll all be roughly that close to the origin at the same time. So that means that the union bound is going to be wasteful. There'll only be sort of boundedly many wrong. So that's why they're sort of off by constants. But you can't capture the distribution by just taking a union bound over your mesh points. So what we have to do is somehow find a way so for each approach, we want to sort of have a way of selecting which point is closest, sort of a representative point that's the closest one among the mesh points, which will be pretty close to the actual minimum, since capital N is sufficiently large. Okay. So this is our problem now, how to capture local minimum. So we need a criterion for selecting which point, sort of a representative that's the closest moment of this approach to the origin. So here's how we do that. So what we do is you can think about, so between each of these points, so each of these is the midpoint of a little interval of width 2/N. And okay, so here I've got that segment. And we're going to take this point rather than say the next one, because the way we tell that this is the best one is that if we linearize the polynomial at this point, so then you get this line, and then you drop a perpendicular from the origin to that line, the place where this perpendicular reaches this linearization happens within this interval, right? So the point is that this segment here, it's roughly flat because so we can get some a priori control on second derivatives. So we can show that at this scale, capital N is sufficiently large. This is roughly a straight line. So when we linearize, our criterion is that this perpendicular here meets the linearization around this point within this interval. Okay. So you can see that wouldn't happen for the next one, say. I put one over here to make it even more obvious. That if you linearize, so we can do this for each point in the mesh, but only one is going to satisfy that. Actually, there's an annoying case where sometimes two neighbors do it, but that's not a big deal. Okay, so this one, of course, it doesn't happen here because you see this. If we draw this line, this is the linearization of the polynomial Okay, maybe it goes a bit above the origin. If you draw a perpendicular from the origin to that line, it's all the way over here, which is not at all within these bounds. So this is our criterion for selecting these points out of all of its neighbors. Okay. Is there any more I can say about the picture? I hope it's clear. Okay. So really, the main point. Okay. The main point is to reduce. So to have a criterion. So reduced to a criterion involving only f and its derivative at mesh points. Okay, so see, this is in terms of the linearization. And so everything, this criterion is completely determined by the polynomial and its derivative at this point. Okay, so we only need that data in order to determine this. And then so then we build our point process. So here's our point process that approximates local minima. So we call it script M. So okay, so on my picture here I've got Z alpha. So this is the alpha point, and this distance here is Z alpha over N. Okay, it's sort of signed, depending on whether the origin is to the right or left as this particle passes, it gives it a sign, but the distance we call Z alpha over N, so that Z alpha is something of order 1, and so those will be the, okay, so I'll say we're going to call our points X alpha, where X alpha is going to be, we'll take this distance Z alpha, but we'll only take it if it meets this criterion, which in terms of this picture is that this Y alpha, which is this displacement from the center of that interval, is at most pi over N, I believe. Okay, and then if it doesn't, so there will be others. So see, we're summing over all N, but we're only going to select the ones that meet this criterion. All the others, let's just put them out at infinity. Okay. Okay, so this is our point process. Is the distances, the local minima are happening at scale 1 over N. We get this process of Z alphas that are very close to those local minima distances. And then we select the ones that meet this criterion of this interval sort of facing, looking at the origin sort of face on. And so this gives us our point process. Okay, and we call that Mn. Okay. All right, so, and now what I'm claiming is, so heuristically, our results are coming from the fact that local minima are roughly a Poisson point process. And so this is the point process that I'll use I'm going to show that this is a Poisson point process, and it very, very closely approximates. I hope I've convinced you that it approximates the local minimum. Okay, so that's our way of finding, that's the point process we've found. So now I'll talk about how we argue that this is a Poisson point process. And first I'll talk about the Gaussian case. So this is just to say a bit about this argument of Yakir and Zeitouni. So it's a really neat argument, and I'll just give a very quick sketch of the ideas. So, okay, so we want to show this as a Poisson point process of the appropriate intensity. Okay, the intensity is the easy part. You can just do a Gaussian calculation that says that for any interval in the real line, the probability that one of these points lies in that interval is root pi over 3 times the length of the interval over capital N plus lower order terms. Okay. Now, and we're summing over capital N points, and so that means that the intensity of this point process is root pi over 3. Okay. All right, so we've got capital N points, probability that any fixed one of them lies in this interval scales like 1 over n with this scaling root pi over 3. Okay, and it also gives tightness. Okay, so this is sort of needed for sort of technical reasons, but okay, so you have tightness of the distribution, which is useful so because they need some compactness argument. The compactness is needed in order to apply the second ingredient. So this is a neat thing that comes from, so this argument was developed by Marek Biskup and Oren Louador when they did their work on the distribution of extremes, so high levels of the discrete Gaussian free field. And this goes back to that literature on maxima for log correlated fields. So they have this strategy to find describe the distribution of extremes of a Gaussian process, and it uses this okay, so this consequence of a theorem of Liggett. All right, so the theorem is quite general, and I don't remember the statement in its full generality. It has this very special consequence. So this is sort of an all UCLA proof. This Marek and Oren and Tom Liggett, the combining forces to study the discrete Gaussian free field. So this consequence is that so this gives a characterization of Poisson point processes of constant intensity. So it says that if the law of a point process, let's just say on R, we're on the real line, is invariant under perturbing each point by IID Gaussians. So just give each point independently a Gaussian kick, then it's a Poisson point process of constant intensity. It doesn't tell you what constant, but it's a constant intensity. Okay, we already learned what the intensity is though. So, okay, so if we can show that this process of approximate local minima is invariant under sort of small independent Gaussian kicks, then we can apply this result of Liggett to say it's a Poisson point process, and we already found its intensity. So now we need to see, well, how can we show that this point process has this property? Where do we get Gaussian kicks? So that we use, here we use the Gaussianity of the field. So what this is a common Gaussian trick, is to let Tn tilde be an Fn tilde. So let's let Fn tilde be an independent copy of Fn, and put Fn hat is just this little rotation. Okay, which, because it's Gaussian, this is equal in distribution to our field Fn. Okay, so here we have a coupling between two identically distributed Gaussian fields. Why do we do this? Well, okay, so we introduce this independent copy. Fn tilde, or Fn and Fn tilde, remember, were of order 1. So this field is of size order 1 over n, which is the scale of the minimum. Okay, so when you're looking at the process of local minima for Fn hat, you can look at it as you have the process of Fn, and then you introduce this other piece that's independent, that is at scale 1 over n. So this is a field of Gaussian kicks. So this field you can view as Gaussian kicks at the scale of our point process. So these are Gaussian kicks, and the only thing that remains to be shown is that these are roughly independent Gaussian kicks. So where does the independence come from? So you can show that near minima minimizers are well separated. So that's just a little argument that to show that with high probability, near minimizers are pretty well separated. And when they're pretty well separated, it's sufficiently far that the field has decorrelated at that length. And that means that these kicks that are at the level of the minimum are roughly independent. Okay, so that's the whole argument. I mean, there's obviously a lot of a lot of technical details, but this is really the overview. Is you peel off this independent piece at the scale of the minima, and then because near minimizers are separated, this is giving you roughly independent Gaussian kicks at your minima. Because this is identically distributed to your field, that means that the point process is invariant. Its law is invariant under these kicks, and then you can apply this theorem of Liggett. And then the intensity calculation tells us this intensity square root of pi over 3. Okay, so I think that's a beautiful argument. So I really wanted to include that. Just in the final few minutes, I want to say a bit about what we then do for the universality. So this problem is somewhat orthogonal. So what we want to do is so to get the distribution of the lowest point, sort of the closest point to the origin, what we'll do is we'll fix a small level and count how many points get below that level. And then we can take moments of that. So if we can prove that the moments of this are universal, then we can get the distribution for the smallest level. So really what it comes down to is understanding the joint distribution of these points at any fixed number of points along the circle. So these, remember, alpha was going from 1 up to capital N. This is this discrete set of points on the circle, or I guess between minus pi and pi. And then we're looking, this sort of is roughly the rescaled modulus of the field at that point. Okay, so, and we want the joint distribution. So if we can show that those joint distributions are universal, then we'll get universality by comparison of moments with the Gaussian case. Okay, all right, so, but it turns out that this is not true. I mean, these joint distributions are not necessarily universal. It is true if these angles are pretty spread out and they avoid roots of unity. You have to avoid roots of unity because of, so I'll just motivate it with a few different points. So here, one root of unity is, okay, we'll look at 0. Okay, so this is e to the I0, which is 1. So 1 is definitely a root of unity. If you look at this field at this root of unity, okay, so this is then just a normalized sum of IID variables. Okay, and this goes to a real Gaussian. Let's say that these are Rademacher, a real Gaussian by the CLT. Okay, so we've got a comparison of the Gaussian case. I mean, this seems fine, you know, this root of unity seems fine, but it does this at the slowest possible rate. Okay, so this random variable here, the distribution only looks Gaussian, so only looks smooth and Gaussian. I mean, of course, if it's Rademacher, it has atoms, but it looks smooth and Gaussian at scales above, if you zoom out above 1 over root n, then it looks like a Gaussian. But if you go and zoom in further than that, then you start to see the atoms. Okay, a similar sort of thing, so if you look at other roots of unity of higher order, it will look Gaussian above some better polynomial scale. But what we really need, so we need the field to look Gaussian at arbitrary polynomial scales, at scale n to the minus c for any fixed constant. So that we really need a very strong central limit theorem. So at arbitrary polynomially small scales, it still has to look smooth and Gaussian, even if these are Rademachers. And we can do that if these points are sufficiently generic in the sense that they're, in a certain quantitative sense, they're not well approximated by rationals with small denominator. Okay, so, and really, what it boils down to, to show a strong comparison with the Gaussian, if you're going to show a strong central limit theorem, as you can imagine, one way to do this would to get really strong control, sort of decay on the characteristic function. And just recall that we reduced our criterion for being for this point being selected as a representative is phrased entirely in terms of the polynomial and its derivatives at these points. So what we need is that for this random vector for any fixed m and any and generic points t alpha 1 up to t alpha m in the circle, we need this vector to have to be very close to Gaussian. But the way we can look at this vector is, so we can just write it as a sum of vectors. So this is 1 over root n plus 1. The sum, 0 up to n. We can pull out these coefficients, and then we just have these vectors, which are these characters. Let's see. Here, j t alpha 1. And then their derivatives. Okay. So this, in terms of the x's, this is a sum. This is a vector valued random walk, and we need this to look like a Gaussian vector at very tiny scales. All right, and that's really the most technical part of the proof, which I don't have time to explain. All I'll say is that once you have a really strong central limit theorem, you can express this event that the field, that these local minima are in any fixed ranges. You can express that as a certain that this random walk lies in a certain domain in phase space. And then you can just approximate that domain with cubes, disjoint cubes, and apply the central limit theorem and add everything up. And so then we get that whatever the answer is for the probability of this, it's going to be the same as it was for the Gaussian. Okay, just as a brief nod to the sort of techniques that go into controlling the characteristic function, this really draws on techniques from this area of additive combinatorics. So there's this whole sub-area of additive combinatorics called the Littlewood-Dawford theory. And the whole theme is to relate the distribution of walks, such as ours. So here we had these vector steps, and then say consider Rademacher coefficients. You want to relate concentration probabilities of this. So that is, if it concentrates too much, if it has a bad small ball estimate, if it concentrates a bit too much in some region, this turns out to correspond to, this happens if and only if the collection of steps has some additive structure, so that the steps have to be special. And then you can separately rule out that your steps have additive structure. So this was a big deal in random matrices, where these steps were coming from a normal vector to a random hyperplane. And you could show with high probability that normal vectors don't have coefficients with additive structure, which leads to really nice properties for these dot products. And in our problem, we have to do a similar thing, but it's a completely different problem, because this isn't a normal vector to a random hyperplane. This is a collection of vectors, a deterministic collection of vectors, and we have to somehow use the quantitative irrationality properties of these points t, 1 up to tm, in order to show the smoothness of distribution. Okay, and I'll just stop there.